So we're starting on page 388, section 6.3, solving linear systems using inverses and Cramer's rule. Invertible square linear systems. This is what we did for bell work. Let A be the coefficient matrix of a system of n linear equations and n variables given by AX equals B, where X is the matrix of variables and B is the matrix of constants. If A is invertible, then the system of equations has a unique solution given by X equals A negative 1B. That's a lot of information, all right? So basically what they're saying in words that mean something, you have some equation that looks like this. You notice they're all capital letters, which means those are all matrices, all right? If I were to have something like 2x equals 6 and just regular old algebra, what do? Divide by 2. There's another way to say division. It's multiplication by the reciprocal, all right? Division is the inverse of multiplication, all right? Division is the inverse of multiplication. That's why you use it to solve. So if I were to multiply by the inverse or use the inverse function here, right? We would say x should equal 1/2 times 6, right? The reciprocal or the inverse function times 6, which gives me x equals 3, right? Easy enough. That's all those words said. If I'm solving for x, that is my matrix, I am just going to take the inverse of A and multiply it by B. And then I should have x, okay? So that's all that's saying. Find the inverse of A and do matrix multiplication, inverse of A times B, and you will solve for the matrix that you're missing and what you're trying to solve for. All right, so let's do it. Use an inverse matrix to solve a coefficient matrix. So my coefficient matrix is exactly what it sounds like. It's a matrix of all my coefficients. My coefficients are 2, -3, that's x and y, and then -3, 5, again, x and y. Okay? And my matrix that I'm solving for is my x, y matrix. All right? My solution matrix is over here, -1, 3 are my answers. All right? So what this is saying is if I need to solve for that missing matrix for my x and y variables, I can just take the inverse of this first guy that's with my variables. Always take the inverse of the one that is with your variables and multiply it by your answers. All right? So then we go back to the steps of finding the inverse. All right? The steps of finding the inverse are first to find the determinant. So the first thing we're going to do is find the determinant of this. All right? My determinant would be 2 times 5, right? 10. Minus -3 times -3. They were nice and they gave us a 1. All right? Second step here is finding the inverse. Again, they were nice, but to find the inverse, you take this and do the reciprocal. 1/1. Again, they were nice. And you multiply it by switching these two that diagonal, 5 and 2. And negating the other diagonal, +3, +3, and multiplying it through. So my inverse is going to be 5, 3, 3, 2.
That's easy.
Okay?
They gave us a good.
Right, they did. So we're going to find my inverse. All right, and then my last step here is to multiply this, the inverse, by the answer one. So my third step here is to take this 5, 3, 3, 2, and to multiply it by my answer matrix. Now, here's the deal. Order matters with matrix multiplication, all right? So you must multiply the inverse times the answer one, all right? You cannot flip it. First of all, it won't work. Second of all, if you try to do it and you do it some weird way, you're going to get the wrong answer, all right? So I'm going to do matrix multiplication here, which means I'm going to do row by column. So I'm going to say 5 times -1 plus 3 times 3. And that's my only row and column there, right? So I'm done with that one. Then I'm going to say 3 times -1 and plus 2 times 3. So I will get 4, 3. This gives me my xy value, this being x, this being y. So my answer to this would be 4, 3. If I were just solving a matrix equation, I would do the same thing, but I would leave it in matrix form. If I'm solving for the variables, x, y, then I would solve and say my x is this and my y is that. So if I plug in a 4, 3 to these equations, it should work, all right? Plug in a 4, 3 to these equations, it should work. 2 times 4 minus 3 times 3 is -1. -3 times 4 plus 5 times 3 is 3, all right? So go ahead and try your guided practice there. 1, A and B. All right, Cramer's rule. Let A be the coefficient matrix of a system of n linear equations and n variables given by ax equals b. Same thing that we have the setup before. If the determinant of A is not equal to 0, that's important, then the unique solution of the system is given by this. And they have all this craziness. Basically what we're going to do is we're going to have a determinant for our coefficients. We're going to have an x determinant and a y determinant. If it were 3 variable, you'd have a z determinant. And then to find x, y, or z, you take your x determinant and you divide it by your coefficient determinant. And so the process is easier than it looks in the description. So let's try the first example here. Use Cramer's rule to find the solution to the systems of linear equations. They use x1 and x2. I'm going to use x and y just for ease of writing it. All right. So we have a coefficient matrix, right? 3, 2, -4, -1. That's my coefficient. And I'm going to use x, y here. And we have my answer. So it's set up very much the same. Okay. What we do is we find 3 determinants. The first determinant that we find is for my coefficients. All right. 3, 2, -4, -1. All right. And then this first column here represents which variable in my coefficients? My x or my y? Assuming that this is x and this is y. Right. So my first column is my x column. So in order to find the determinant for my x, I'm going to replace that x column with my answers. So I'm going to replace this x column with 6, negative 13, and I'm going to leave that y column alone. All right? Replace the x column, leave the y column alone. And then I should do the same thing for a y. So I need to find a determinant for y. For this one, I'm going to leave my x column alone for my original, and I'm going to replace the y column with my answers, 6, negative 13. So I am looking for 3 different determinants, okay? 3 different determinants, which are very easy to find. All right, so to find these, I just do my determinant process. 3 times negative 1 is negative 3, minus negative 4 times 2, negative 8. So negative 3 minus a negative 8 gives me what? 5. So that's the determinant for my coefficients. Let's find the determinant for my x. 6 times negative 1, negative 6, minus negative 13 times 2, negative 26. So that's going to give me a 20 for that determinant. And then for my y, 3 times negative 13 minus negative 4 times 6. So that gives me negative 15. So I found my 3 determinants, all right? And now I'm going to do one more step to actually solve for my x and y. To solve for x and y, x is going to be my x determinant divided by my coefficient determinant. So my x determinant is 20. I'm going to divide that by the 5. So my x is 4. For my y, I'm going to take my y determinant and divide by my coefficient. So I'm going to say negative 15 divided by 5 gives me negative 3. So my answer here is 4, negative 3.
And we don't put